I'd like to give you a brief overview of the energy efficiency and energy demand at the Port of Los Angeles. If I can work this, there you go. Most of our users are cargo terminals. As you saw in Luskin report, about 50% of our load is cargo terminals. Cargo terminals so far have had this particular load centers. We have the wharf cranes, we have terminal automation, we have shore power, we have terminal lighting, we have building and facilities, we have reefer outlet rows, and then some miscellaneous loads such as security, access, gate control, and miscellaneous. The electrical load in a cruise terminal, we have one cruise terminal in Port of Los Angeles, are similar, but they are in different categories. We have majority of the load is the building and facilities. We have large air conditioning load and large lighting load in the building. Then nowadays we have the shore power or alternative maritime power as mentioned for this large cruise liners that come in. We do have automated passenger gangways and they're electrically driven. We do have large parking lots which require lighting. We have some electrical equipment such as forklifts and other manually driven equipment that they handle baggaging and stores, transfers and so forth. They are all electric. Sometimes they are also gas. So if they are electric, then they need chargers. And also we have miscellaneous loads such as security, access control, and gate facilities. The AMP program, or Alternative Maritime Power, is basically a very simple concept. It's just like plugging your hairdryer in the wall, except it's not hairdryer. It's a huge ship, and the loads are very, very large. So what we envisioned to do about 10, 15 years ago, to put, very simply, to go to a utility source, get a service, put the electrical equipment, transformers and switchboards and control equipment, go to protection, and then go to an outlet. And then when the ship comes, ship has a extension cord, if you will. We call them cable management system, that drops in and connects to the power outlet, and we turn the switch on, and voila, the lights are on. Well, it's much simpler said than done. What we did is, about 2003, we came up with the first generation. This is the latest. This is not the Fred Flintstone style that we used to do. This is the real deal. What we have is on the shore, we have a pit, and we have two connections, two cables. And why two? A, because of the load, B, because of redundancy. So we have two connectors. Each connector is about 35 to 40 pounds. It's a little bit larger than your typical hairdryer. And so these cable management is on the ship, on the container vessels. They drop the cables. Then the shore end gets plugged into the system. The ship end gets plugged into the ship switchboard. And then we go to the switchboard, and after the automation is cleared everything, we turn the switch, and the electricity flows from here, through here, to here, and the ship is on power. On the cruise vessel, concept is very similar, except the cable management is on shore. It's not on the ship. And the reason is because, first of all, the cruise vessels didn't want to have this cable management taking space that they can sell to the happy cruiser. And so they did not want any cable management taking room on board. So we put them on the shore. Also, cruise liners, each cruise liner is a world of its own. They have their cable entry in a different place. Every ship is different. There are no two similar ships. Even the sister ships, they sometimes are different. So, and also if you notice, the cable entry is more like a human scale height, rather than the other ones were about 60 feet up in the air. And so we used gravity to help us to drop those cables. In this case, we had to work against gravity to put the cable in, although we didn't have to go too far. So we came up with a flexible cable management system on a truck, which has a flexible arm, which pan, tilt, zoom, and comes up and down. We innovated this, and we called it Ampmobile. just like the Batmobile. It's trademarked, by the way. Don't you get any ideas, you entrepreneurs? But the ship, cruise vessel, is a different world. It has much larger loads than the usual container vessel. The cruise vessel is about anywhere between 10 to maybe 18 megawatt, depending on the size. What we have seen in the Port of Los Angeles, I have seen about up to 13 megawatts of actual power taken from the system. To translate that 13 megawatts of power from shore all the ship, we need to have 4 connectors, and these are larger connectors, and we have some special treatment of the grounding and the neutral connection. So this became a much larger and a much more expensive installation than your typical container ship outfit. So we have the same concept. Power comes from the shore, goes to this cable management, gets transferred to the ship, gets plugged in, and then we turn the ship on. As mentioned, all the red dots are the wharves that are right now energized with AMP or AMP vaults. The yellow ones are perhaps future. Now, you think AMP is an energy hog. When automation comes in, it's going to dwarf AMP. In AMP systems, we will probably need anywhere between 1.8 to maybe 2.5 megawatts per container yard, per ship. When automation comes in, each terminal requires 20 megawatts. That's the type of the deal that we are talking about. Automated terminals are terminals where, by definition, a container handling equipment is operating without the human interaction for the length of the duty cycle of the equipment. In plain English, it's plug and play. This is an actual pictures of automated terminal. In the rail, we have, if you see the overheads, there are cranes, large cranes over the rail that transfer the container from the transfer vehicle onto the rail. And that could be electrified. And it is electrified, for example, in Norfolk, Virginia. And in the backland, we have this stacking area where the containers are stacked through use of this automated guided vehicles, which are all electric. They bring the container here, the water side crane picks it up, puts on a stack, then the land side crane picks it up and puts on a truck, and the truck rolls away. It's all automated. And I'll show you a little bit of that in a further slide. We have one terminal in Port of Los Angeles, and we have the similar terminal in Port of Long Beach. In Port of Los Angeles, we have tray pack at berth 142, 147, right now under construction for this automation. We are currently in the process, the early process of starting construction of this portion. These portions are pretty much done, and the test bays are already under commissioning and testing. We will have 48 of these cranes. This is all automated area. There is no human intervention in this part. And if somebody were to open the fence and get in, guess what? The power is going to cut to that fenced area for safety purpose. So I wouldn't suggest you go in there without any prior notification. Here's a map. The top is a plan view. You're looking from the top. The bottom is you're looking up. That's a sectional view of the operation and the automation process. Here's the ship at the dock, and the blue is the manual or human-driven process. The key crane or the wharf crane picks up the container manually and puts it on a platform. Then the operation of the automated process takes over. A guided vehicle takes that and puts it on the stacking area, and then a stacking crane, ASC, a water side, picks that up, puts them on a stack. Then a stacking crane on the land side picks it up and prepares for the either a truck or on a rail area. Now this portion from the outside a stack to the rail can be manual, or it could be also automated. I have a little slide here that just animates and tells you how the automation works. If I can get this thing loose. I hate Mike. There. You see, the crane picked it up. It's going to put down on a platform. AGV is going to come in, pick up that container. It's all computer driven. And it's going to follow a magnetized pattern on the terminal flooring. And then brings it up, drops it in. The water side ASC picks it up and rolls back, puts in a predetermined stack prepared for it prior, and then the land side crane picks it up and puts it on this truck platform. In order for this to drop in, the driver, we don't show it here, the driver has to get out and get in that red booth. And the laser guided technology puts it exactly on the truck driver gets out of the booth, gets in there, then it unlocks and it drives out. So this is all automated. So our computers better work. Or power better be on. All right. So all this is power dependent. As mentioned, the existing Polar power footprint is estimated to be 65 MVA. And you'll ask me, how do you estimate that? Well, it's a simple formula. We have one cruise terminal. We have 7 cargo terminals. Our average cargo terminal is about 8 megawatt, non-automated. So if you add them up, it's about 65 MVA, now plus and minus. Amp, we have about 23 cargo amp berths. Let's say give them the benefit of doubt of maximum use, 2.5 megawatt each, 60% occupancy. That means 60% of them are connected at any time, which is very high. And 80% connection requirements per state, so that translates to be about 35 MVA. Here comes the automation. You see the automation is 90 MVA. If you have, let's say, 5 cargo terminals, each one of them 15 MVA, that's your 90 right there. So I averaged about 6 container terminals. Every one of them is 15 megawatt actual power. That's 90 MVA. Total power projected power demand is 190 MVA. That's a lot of MVAs. So we are going to be dependent on energy. And this energy has certain characteristics. At the Port of Los Angeles, we have come up with a plan, or we are working towards it. As a matter of fact, today we have a meeting to go over this very plan to make sure that we have thought of all the possibilities. We call it EMAP, Energy Management Action Plan, and it has its 5 major pillars. The first one is power resiliency. This is the thought that an operation should be able to stand up and start rework after a catastrophic event or power loss. So how resilient is an operation depends on all the functionalities that have to come up to make it minimally functional. That's called the power resiliency. What do we need on our power system to make a system to come up? Second is power availability. Is the quantification of and management of the power demand for today's power demand and also for future projection of the power demand. Can we have that much power? You may have generation capacity, but can that generation capacity be transmitted onto the site and via what conduits, what lines, what transmission medium is that power going to be available to the users? Today's availability of our distribution network on a utility level is the yesteryear's system. Have you ever seen new power poles going on? Have you ever seen new large-scale power distribution system, transmission system? No. All the power companies are working in the NIMBY fashion. You know what NIMBY stands for? Not in my backyard. Nobody wants the power stuff in their backyard. Put them on a neighbor's backyard. So power availability is a very delicate subject. It has many facets. Next, we are worried about power quality. Okay, power is on our backyard and we have the power, but what kind of power? Is this power, quality of the power, is it to our needs? Is it going to go down? Does it have the necessary wattage that we want or MVA that we want? How is it delivered? Is it on vulnerable to balloons or birds or accidents, or how's the routing, or is it on a truck route? Every other day I have a bird going through a power line or a truck hitting a power line, and so the quality can suffer because of those. Then we are talking about cost effectiveness. As mentioned last speaker, we have this double whammy of demand is going up, at the same time cost is going up also. Last year, Department of Water and Power increased their rates 5.5% for next 2 years. So next 2 years we'll have to pay 11% more than what we're paying today. And then sustainability. We want to be green, we want to be sustainable. Some of that power should be coming from non-fossil fuel sources. And in order to integrate that renewable power in our power demand, that also creates, on the surface it sounds good, but it does have its difficulties, logistical issues, and some other challenges that we all have to face in order to bring and integrate power sustainability in our systems. Energy efficiency is the lowest hanging fruit right now. As you saw, 1/3 of a cargo terminal load is its lighting. And we have embarked in Port of Los Angeles to install LED-based high-mast systems. We have successfully installed the very first world's terminal that has LED lights. Big Long Beach. So we have a sample backyard where we can measure it, when we can see it, where we can tweak it and make it as our energy efficient high-mast lighting system that we have envisioned all these years. So that's the lowest hanging fruit. That's immediate. We can apply that. The problem there is the financial. It is not as inexpensive as you may think it is. We're working on it. Some manufacturers are working on it very hard, and so the future is bright. We could use some power factor improvement for the non-EEs in the audience. That's like beer and foam. Have you ever had beer with no foam? That's no fun. And when you pay for a mug of beer, it better be beer, not just foam, right? So the power factor is the foam. You want to manage that foam. You need to have a little bit of a kVAR in your system, but not too much. Power factor improvement is a very basic electrical, it's not efficiency, but okay, for the sake of non-EEs, we'll call it efficiency. We can improve the power factor by putting some capacitors on the reefer outlet racks or wherever there's a motor running. The motors are notorious in their low power factor. We have to increase them so that we won't waste energy, the energy that does work. We can have also some power monitoring and control systems. We have employed some SCADA systems in our distribution network that gives the user the opportunity to look at their power distribution, to look at their power demand areas, to look at the price and cost and peak shaving, what's their bottom base demand, what is the daily power profile, how can they shift some loads during the day to save energy and to not to hit the high cost time frames where they have to pay during the day is much more expensive to charge your batteries than if you had to charge during the evening. So this monitoring and control systems have been incorporated in our design and in our power distribution systems for at least 10-15 years. All of our terminals are fitted with those. It's just the challenge is to get the terminal operators enough incentives for them to sit down and use it. You need to learn the software, you need to learn the system, and use it to your advantage. Also, we have been very active in our energy efficient building design, the LEED program. Our architects are masters of those. We're employing all kinds of energy efficiencies in our buildings, and we certify them for the LEED certifications. Solar photovoltaic, we are under certain demand to have about 10 MVA of solar photovoltaic. We are happy to report that we are making progress. We have about shy of 2 MVA already. 1 MVA is on the cruise terminal roof. The others are scattered on some buildings, and we are in process to work with Water and Power to avail some real estate or rooftops for them to come in and put the photovoltaics at their cost, for their operation, for their ownership, and to directly connect to the lines. What's the future? Well, some people have some ideas. We have some ideas of wind energy. Unfortunately, we don't have too much winds. This is not really a wind country. But we are right now doing some studies to see where we're at. We do have some very calm areas around the port, so it really doesn't help us with the wind energy. But others have also been looking to harvest some of the wave energy. These are the futuristic thinkings that are right now being tossed around. By that, I conclude my presentation, and we will take questions at the end. Thank you.